Look up at the night sky and you'll see it, just a tiny dot of light. We call it our closest neighbor, but that's almost a joke. Alpha Centauri is 4 light years away. 4 light years. To put that in perspective, that's 25 trillion miles of nothing but empty space. And here's the thing, it's not even one star. It's 3 stars locked in this wild gravitational dance, and somewhere in that system, there might be a planet we could actually live on. But getting there? That's where things get insane. Because the distance between us and Alpha Centauri isn't just far. It's the kind of far that breaks your brain when you really think about it. Today, we're going to explore what it would actually take to reach the closest star system to Earth. And trust me, the answer is way crazier than you think.
Deep within the southern skies, below the celestial marker of the Southern Cross, a single point of light pierces the darkness with an intensity that rivals the brightest beacons of the cosmos. To the unaided eye, standing on the plains of the Atacama or the beaches of New Zealand, this object appears as a singular, unwavering star, the third brightest in the entire night sky. It has served as a navigational anchor for Polynesian wayfinders and European explorers alike, a fixed point in the turning heavens that signaled the way south. This is Rigil Kentaurus, the foot of the Centaur, known more commonly to the modern world as Alpha Centauri. While it hangs static in the velvet backdrop of space, the serenity of this light is a deception born of immense distance. The human mind struggles to calibrate the scale of the void that separates us from this neighbor. We speak of it as being close, using the term neighbor to imply a proximity that feels tangible, yet this closeness is a relative concept that defies terrestrial logic. On Earth, a neighbor is someone across the street or over a fence. In the galaxy, a neighbor is an entity separated by a gulf so profound that the fastest object our species has ever built would require tens of thousands of years to cross it. The light hitting the retina of an observer tonight left its source over 4 years ago, traveling at the ultimate speed limit of the universe. 300,000 kilometers every single second, without pause to bridge that gap. We are looking at a ghost of the recent past, a snapshot of history constantly arriving 4 years late. This star system has held a privileged place in the imagination of astronomers long before they understood its true nature. In the 2nd century, Ptolemy catalogued it, and for millennia it was just another bright mark on the celestial sphere. It was not until the late 17th century that Jean Richaud, observing from India, peered through a telescope and realized the single star was actually 2. The singular point of light split, revealing a duality that hinted at the complex gravitational ballet occurring in the dark. It became the finest binary star in the sky, a jewel box of stellar physics that promised to unlock the secrets of mass and orbital mechanics. Later, a third, much fainter member was discovered, turning the binary into a trinity and complicating the picture of our nearest stellar family. The question that haunts the scientific community and the dreamer alike is not just what these stars are made of, but what the distance between us truly represents. To say it is 4.37 light-years away is a mathematical statement, but to feel that distance is an emotional and cognitive challenge. It represents the boundary between the known and the unknown, the shore of our solar system and the open ocean of interstellar space. Standing at the precipice of this distance, we are forced to ask what it would take to bridge it, and what waits for us on the other side. The journey to Alpha Centauri is not merely a trip across space, but a journey across the limits of human engineering and the horizons of our comprehension. Dominating the system is Alpha Centauri A, a star that feels uncannily familiar. It is a yellow dwarf of spectral type G2V, almost a mirror image of our own Sun. It possesses nearly the same mass, the same radius, and the same luminosity, burning with a steady, reassuring light that would make it indistinguishable from Sol if viewed from a hypothetical planet in orbit. It is slightly older than our Sun, perhaps by 1 billion years, suggesting a maturity and stability that is enticing to those hunting for long-lived planetary systems. This is the primary anchor of the system, the gravitational heavyweight that dictates the motion of its partner. Dancing with this solar twin is Alpha Centauri b, a star of a different character. It is a K1b orange dwarf, smaller and cooler than its primary companion. With about 90% of the Sun's mass and shining with a distinct orange-hued visible light, it emits less energy but offers a different kind of stellar environment. These two stars, A and B, are locked in a gravitational embrace that sees them orbit a common center of mass every 79 years. Their path is highly elliptical, a stretched loop that brings them as close as the distance between Saturn and the Sun and swings them out as far as Pluto. This dynamic movement means that any planets orbiting these stars must contend with a shifting gravitational landscape, where the second sun in the sky grows bright and dim over the course of a human lifetime. Drifting far from this central waltz is the third member of the Trinity, Proxima Centauri. It is a red dwarf, a class M flare star, and it is the true holder of the title for closest star to Earth. Proxima is a fraction of the size of its larger cousins, with a mass only about 12% of the Sun, barely larger than the planet Jupiter. Yet, it is dense and volatile. It orbits the main pair at a tremendous distance, roughly 13,000 astronomical units away, taking over 500,000 years to complete a single circuit. For a long time, astronomers debated if it was truly gravitationally bound to A and B or just passing through, but recent measurements confirm it is the prodigal third sibling tethered by the feeblest of gravitational threads. The interaction between these three bodies creates a complex environment unlike anything in our solitary solar system. The gravity of A and B churns the space around them, creating exclusion zones where planets cannot form or would be ejected into the dark. Meanwhile, Proxima, despite its small stature, is a violent neighbor. It is prone to magnetic outbursts and stellar flares that can increase its brightness significantly in a matter of minutes, blasting the surrounding space with high-energy radiation. This trinity presents a study in contrasts: the stable, sun-like A, the cooler, reliable B, and the chaotic, dim Proxima, all bound together in the emptiness, influencing one another through the invisible, relentless tug of gravity. To understand the chasm that separates Earth from this triple star system, one must grapple with the concept of the light year, a unit of measurement that is often misused as time, but is strictly a measure of distance. A light year is the distance a photon of light travels in a vacuum over the course of one Earth-Julian year. That distance is approximately 9.46 trillion kilometers. When we say Alpha Centauri is 4.37 light-years away, we are talking about a journey of over 41 trillion kilometers. These numbers are so large, they become abstract, slipping off the surface of the human mind without leaving a scratch of comprehension. We can attempt to visualize this through analogy. If the Sun were reduced to the size of a standard grapefruit placed in New York City, the Earth would be a grain of sand orbiting just a few meters away. On this scale, Alpha Centauri A would be another grapefruit located not in New Jersey or even Pennsylvania, but all the way in San Francisco. The space between these two grapefruits is not empty air, but a void so absolute and vast that the human brain lacks the evolutionary hardware to intuitively grasp it. Between the grain of sand in New York and the grapefruit on the West Coast, there is nothing but dust and radiation. Consider the speed of light itself. A beam of light can encircle the Earth 7.5 times in a single second. It takes light just over 1 second to reach the Moon, and about 8 minutes to travel from the Sun to the Earth. To reach Pluto, light must travel for over 5 hours. Yet, to reach our nearest stellar neighbor, that same beam of light must travel continuously without stopping for 4 years, 4 months, and roughly 10 days. Watching a simulation of a photon leaving our Sun, one would have to sit and watch the screen for over 4 years just to see it arrive at Proxima. Astronomers and physicists often describe the frustration of communicating this scale. When we look at the night sky, the stars appear as a flat canopy, equidistant and close. We lack the depth perception to see the abyss. The fastest speed a human being has ever traveled relative to Earth was achieved by the Apollo 10 crew, reaching nearly 40,000 kilometers per hour. At that record-breaking speed, it would still take over 100,000 years to reach Alpha Centauri. History would rise and fall, civilizations would crumble and be reborn, and the spacecraft would barely have traversed a fraction of the distance. The gulf is a barrier of time as much as it is of space, turning the concept of travel into a multi-generational odyssey. In August 2016, the European Southern Observatory made an announcement that fundamentally shifted our perspective on the Alpha Centauri system. After years of meticulous observation, sifting through the subtle wobbles of Proxima Centauri caused by the gravitational tug of an unseen companion, they confirmed the existence of a planet, Proxima Centauri b. This was not a gas giant or a frozen wasteland far from its star, but a terrestrial world, likely rocky, with a minimum mass of 1.3 times that of Earth. Most tantalizing of all, it orbits within the habitable zone of its star, the region where temperatures could theoretically allow liquid water to exist on the surface. The discovery ignited a firestorm of speculation and scientific inquiry. Proxima b orbits its star at a proximity that would be terrifying in our own solar system, completing a full year in just 11.2 Earth days. It sits only 7.5 million kilometers from the red dwarf, closer than Mercury is to our Sun. However, because Proxima Centauri is so cool and dim, this close orbit places the planet in the temperate zone. The sunlight it receives is redder, shifting the palette of the world into hues of crimson and infrared. If plants exist there, they might appear black or purple to our eyes, evolved to absorb the weak output of their sun. However, the term habitable zone does not guarantee habitability. The conditions on Proxima b are subject to the violent temper of its parent star. Red dwarfs are active, and Proxima is known to unleash superflares that could strip the atmosphere from any orbiting planet. The planet is also likely tidally locked, meaning one side faces the star in perpetual day while the other is frozen in eternal night. This would create a world of extremes, with a scorching day side and a freezing night side, separated by a twilight terminator zone where life might cling to existence in the shadows. Winds could roar across the surface, redistributing heat in a global storm system driven by the stark temperature difference. Studying this world presents a monumental challenge. Due to the blinding glare of the star, we cannot yet photograph the planet directly. We know it exists only through its shadow and its gravity. We do not know if it has an atmosphere, a magnetic field, or water. It remains a silhouette of data, a collection of numbers that suggest a world but do not yet reveal it. Future observations are currently being planned, utilizing the next generation of space and ground-based telescopes to sniff the spectrum of light passing near the planet, hoping to detect the chemical fingerprints of oxygen, methane, or water vapor that would signal a living world. The dream of visiting Proxima b and the binary pair of Alpha Centauri crashes hard against the reality of our current engineering capabilities. Conventional chemical rockets, the workhorses that took humanity to the moon and sent probes to the outer planets, are woefully inadequate for interstellar travel. The tyranny of the rocket equation dictates that, to go faster, you need more fuel, but carrying more fuel makes you heavier, requiring even more fuel to move the mass. To reach Alpha Centauri in a human lifetime using chemical propulsion would require a fuel tank larger than the observable universe. We are effectively becalmed in the cosmic ocean, drifting on rafts when we need ocean liners. To bridge the gap, scientists and engineers are looking toward physics that bypasses the need for heavy propellant. One of the most prominent proposals is the Breakthrough Starshot Initiative. The concept abandons the idea of massive ships filled with astronauts in favor of swarms of tiny gram-scale probes attached to incredibly thin, reflective light sails. Instead of carrying engines, these sails would be pushed by the pressure of light itself, generated by a colossal array of ground-based lasers on Earth. By focusing gigawatts of power onto a sail for a few minutes, the probe could be accelerated to 20% of the speed of light. At this velocity, the travel time shrinks from millennia to just over 20 years. A probe launched today could theoretically beam back images of Proxima b within the lifetime of the designers who built it. However, the technical hurdles are staggering. The laser array would need to be miles wide and capable of firing with perfect precision through the turbulent atmosphere of Earth. The sails must withstand the intense heat of the laser beam without vaporizing, and the tiny electronics must survive the deep freeze of interstellar space and the bombardment of cosmic dust impacts, which at relativistic speeds would hit with the force of bullets. Other concepts exist, such as nuclear pulse propulsion or fusion drives, which would detonate nuclear explosions behind a spacecraft to ride the shockwaves. These designs offer the ability to carry heavier payloads, perhaps eventually humans, but they require technologies that are currently beyond our grasp or banned by international treaties. The energy requirements for any interstellar mission are astronomical. Accelerating a single ship to a fraction of light speed consumes more energy than entire nations produce in a year. We are in the infancy of this engineering endeavor, sketching blueprints for cathedrals of technology that our grandchildren may lay the foundations for. The question of life in the Alpha Centauri system extends beyond the rocky surface of Proxima b. It challenges our understanding of how planetary systems form and evolve in the chaotic environment of multiple stars. In a single star system like ours, the disk of dust and gas that forms planets is relatively undisturbed. In a triple system, the gravitational interference of the companion stars acts like a cosmic blender. For planets to form around Alpha Centauri A or B, they must exist in stable orbits close enough to their parent star to avoid being pulled away by the companion, yet far enough out to not be roasted. Theoretical models suggest that stable zones do exist around both A and B. A planet orbiting Alpha Centauri A at roughly the same distance Earth orbits the Sun would likely be stable for billions of years. The view from such a world would be surreal. The primary sun would traverse the sky much like ours, but the secondary sun, Alpha Centauri b, would appear as a brilliant, diamond-like light, visible even in the daytime, waxing and waning in brightness as it moved through its 79-year orbit. The nights would rarely be truly dark when the secondary star is in the night sky, casting double shadows and influencing the circadian rhythms of any potential biology. The atmospheric dynamics of a planet under two suns would be complex. The varying insolation could lead to strange climate cycles, with eras of intense heat followed by cooler periods depending on the alignment of the stars. Life, if it evolved here, would need to be robust. Photosynthetic organisms might evolve to harvest light from two different parts of the spectrum, utilizing the yellow light of A and the orange light of B. The radiation environment is also a critical factor. While A is quiet, B is more active, and Proxima is a flare star. A planet in this system would need a strong magnetic field to protect its atmosphere from being stripped away by stellar winds. Search efforts are ongoing to find these hypothetical siblings to Proxima b. Astronomers are using advanced coronagraphs to block out the blinding light of the stars to look for the faint specks of planets. While Proxima b steals the headlines, the Holy Grail remains an Earth twin orbiting Alpha Centauri a world that would be bathed in the same warm yellow light that nurtures life on Earth. Such a discovery would fundamentally change the calculus of life in the universe, proving that habitable worlds can thrive even in the complex gravitational knots of multiple star systems. As we look toward the future, the Alpha Centauri system stands as the primary target for the next great leap in astronomy. We are currently in an era of construction for the largest eyes humanity has ever built. The extremely large telescope under construction in the Chilean desert will possess a primary mirror 39 meters across. With this immense gathering power, it may be capable of directly imaging the planets of the Alpha Centauri system, separating their light from the glare of their stars and analyzing their atmospheres for biosignatures. This is the threshold of a new age, where we move from detecting planets to characterizing them as worlds. Emerging technologies are also beginning to close the gap between theory and reality. Advances in materials science, particularly in the realm of light sails and metamaterials, are bringing the concepts of the Starshot initiative closer to feasibility. Artificial intelligence is allowing us to sift through the noise of stellar data to find the tiniest signals of orbiting worlds that human eyes would miss. We are building the intellectual and physical infrastructure to reach out and touch our neighbor, not just look at it. The role of Alpha Centauri in humanity's future is pivotal. It represents the first step out of the cradle. If we can reach this system, we prove that we are not bound to the rock of our origin. It serves as a focal point for our aspirations, a challenge that demands global cooperation and long-term thinking. The mission to Alpha Centauri is a multi-generational project that forces us to think beyond election cycles and fiscal quarters, looking instead towards centuries and millennia. There is a profound philosophical implication in reaching these stars. Finding life, even microbial life, on a planet next door would imply that the universe is teeming with biology. Finding nothing, finding a trio of dead stars and barren rocks, would be equally profound, highlighting the precious rarity of the Earth. As the piano notes of the cosmos play on, we stand on our small blue marble, looking across the 4-light-year void, realizing that Alpha Centauri is not just a destination, it is a mirror. In seeking to understand it, we are really seeking to understand our own place in the grand, silent neighborhood of the galaxy. To understand this neighborhood requires stripping away the romanticism of the night sky and confronting the fusion engines powering it. The system is not merely a destination, but a complex gravitational mechanism, a three-body problem played out on a scale that dwarfs human comprehension. The primary star, Alpha Centauri A, officially named Rigil Kentaurus, is a G2V star, a spectral classification that makes it nearly a twin to our own Sun. It possesses 110% of the Sun's mass and 150% of its luminosity. If one were to stand on a hypothetical planet orbiting this star, the light would feel familiar, a warm yellow-white radiance that mimics the conditions under which life on Earth evolved. It is this uncanny resemblance that first drew astronomers to it, creating the illusion that a mirror image of our solar system might exist just across the precipice of interstellar space. Yet the similarities end with the primary star, for Rigil Kentaurus is locked in an eternal elliptical waltz with Alpha Centauri b, a K1b orange dwarf. This companion is smaller, cooler, and dimmer, shining with only 50% of the Sun's luminosity. The dynamic between these two bodies creates a gravitational environment entirely alien to our experience. They do not orbit a fixed point in empty space so much as they pivot around a common center of mass, swinging in a highly eccentric path that brings them as close as 11 astronomical units and as far apart as 36 astronomical units. To visualize this, imagine our Sun having a companion star that swings in as close as Saturn, blazing in the sky like a second smaller sun before retreating out to the distance of Pluto over a period of 80 years. This proximity means that any planet orbiting either star would have to contend with the gravitational perturbations of the other, a celestial tug-of-war that complicates the formation of stable planetary orbits and challenges the stability of climate systems over geological timescales. Then there is the third member, the outlier that challenges our definitions of the system itself. Proxima Centauri sits a staggering 13,000 astronomical units away from the central pair, a distance so vast that it takes 55 days for light to travel from Alpha Centauri A to Proxima. For decades, astronomers debated whether Proxima was truly gravitationally bound to the pair or merely passing through the neighborhood. It is a red dwarf, a Class M flare star, barely larger than Jupiter but possessing a density that crushes matter into a state of terrifying compactness. It glows with a dull, ruddy light, invisible to the naked eye from Earth, despite being the closest star to us. Its surface is a tempest of magnetic activity, prone to violent outbursts that can increase its brightness by magnitudes in a matter of minutes, bathing its orbiting planets in lethal ultraviolet and X-ray radiation. This is the irony of our nearest neighbor. The closest star is a volatile, dim ember that offers the most hostile environment imaginable, yet it holds the most promising candidate for an Earth-sized planet in the habitable zone. The scale of the distance to this trinary system is a concept that the human mind struggles to codify without relying on abstract numbers. We say 4.3 light-years, but the number 4 is deceptively small. To truly grasp the scale, we must look at the history of how we measured it. A saga of geometry and patience that spanned centuries. The quest to measure stellar parallax, the apparent shift of a star against the background of more distant stars as the Earth moves around the Sun, was the holy grail of 19th century astronomy. It was the Scottish astronomer Thomas Henderson, working from the Royal Observatory at the Cape of Good Hope, who first captured the elusive shift of Alpha Centauri. The angle he measured was less than 1 arc-second, a microscopic sliver of geometry equivalent to measuring the width of a human hair from 2 kilometers away. This tiny angle revealed the terrifying truth of the void. It proved that the stars were not painted on a celestial sphere just beyond Saturn, but were distant suns separated by chasms of emptiness, so profound that light itself grew tired crossing them. Henderson's revelation shattered the cozy, claustrophobic universe of the past and replaced it with a cosmos of isolating immensity. To bridge that gap with our current technology is an exercise in humility. The Voyager 1 probe, the fastest object ever launched by humanity, travels at 17 kilometers per second. At this speed, it would take over 70,000 years to reach Alpha Centauri. If Voyager had been launched by the first humans to walk out of Africa, it would only now be arriving. This time frame renders traditional chemical propulsion useless for interstellar exploration. The tyranny of the Tsiolkovsky rocket equation dictates that to go faster, we need more fuel, but that fuel adds mass, which requires even more fuel to accelerate. It is a logarithmic trap that binds us to the solar system, preventing us from ever reaching the stars with the fire that brought us to the moon. To break this deadlock, we must abandon the idea of carrying our propellant with us. We must look to physics that circumvents the rocket equation entirely. This brings us to the concept of light sails and directed energy propulsion, the core philosophy behind initiatives like Breakthrough Starshot. The premise is elegant in its simplicity, but brutal in its engineering requirements. Instead of a massive ship filled with fuel, we construct a probe weighing no more than a few grams, attached to a sail made of material so thin it is measured in atoms. We then leave the engine at home, constructing a massive array of lasers on Earth or the Moon, capable of combining their beams into a single coherent column of light with the power of a nuclear power plant. When this beam hits the sail, the momentum of the photons transfers to the probe, accelerating it not with chemical explosions, but with the pressure of light itself. The physics of this acceleration are violent. To reach 20% of the speed of light, the target velocity for a mission to Alpha Centauri within a human lifetime, the probe must endure acceleration forces of 60,000 g-forces. The sail must reflect 99.99% of the incoming laser energy, for if it absorbs even a fraction of a percent, it will instantly vaporize into a cloud of plasma. The material science required to build such a sail does not yet exist. We are talking about metamaterials, perhaps graphene-based sandwich structures that interact with light at a specific wavelength while maintaining structural integrity against the bombardment of interstellar dust. Even a grain of sand colliding with the probe at relativistic speeds would deliver the kinetic energy of a stick of dynamite, obliterating the mission instantly. This necessitates a fleet strategy where we launch not one, but thousands of these nanocraft, assuming that the vast majority will be destroyed by the interstellar medium, sacrificed so that a handful might survive the 20-year journey to transmit a signal back home. The journey through the interstellar medium is not a trip through empty space. The void between the Sun and Alpha Centauri is filled with the debris of galactic history. There are clouds of ionized hydrogen, stray cosmic rays, and the leftovers of supernovae that exploded millions of years ago. As we leave the protective bubble of our Sun's heliosphere, we enter this interstellar wind, the heliopause. The boundary where the solar wind meets the interstellar medium marks the true edge of our dominion. Beyond this lies the Oort cloud, a spherical shell of icy bodies that extends nearly a light-year out, the graveyard of the solar system's formation. Traversing this region means navigating a minefield of dark comets and ice shards, invisible to telescopes until it is too late. The silence of this space is absolute, a vacuum where sound is impossible, yet it is alive with radiation, a constant sleet of high-energy particles that would shred human DNA and fry unhardened electronics. When the survivors of this relativistic armada finally approach the Alpha Centauri system, they do not stop, they cannot stop. Without a laser array at the destination to slow them down, they will streak through the system at 60,000 kilometers per second. The entire encounter, the culmination of decades of work and centuries of dreaming, will last only a few hours. In that brief window, cameras and sensors must wake up, lock onto their targets, and gather as much data as possible before the system recedes into the darkness behind them. They will attempt to image the planets, analyze their atmospheres spectrally, and measure their magnetic fields. The data they collect will then be beamed back to Earth using a laser on the probe, a signal so faint that detecting it will require a telescope the size of a kilometer, staring at the exact spot in the sky where the probe was 4 years ago. The target of this fleeting flyby is Proxima Centauri b, the planet that has captured the imagination of exoplanet hunters since its confirmation. It sits in the habitable zone of the red dwarf, at a distance where liquid water could theoretically exist on its surface. But habitable is a relative term in astrophysics. Because Proxima is so dim, the planet must orbit dangerously close to the star to receive enough warmth, completing a full year in just 11 Earth days. This proximity likely locks the planet in a tidal embrace, keeping one face eternally pointed at the star and the other frozen in perpetual night. The day side would be a scorched desert under a crimson sun that never sets, while the night side would be a frozen wasteland of eternal ice. Between these two extremes, along the terminator line where day meets night, a twilight zone might exist, where temperatures are mild enough for liquid water and perhaps life to endure. However, the atmosphere of Proxima b is a subject of intense debate. The relentless solar wind and coronal mass ejections from the volatile parent star may have stripped the planet of its atmosphere billions of years ago, leaving it a barren rock similar to Mercury. Alternatively, if the planet possessed a powerful magnetic field, it might have retained a thick atmosphere, perhaps even an ocean. Computer models suggest scenarios ranging from a water world completely covered in a global ocean to a dry, Mars-like desert. The color of the light from the star, primarily in the infrared spectrum, would mean that photosynthesis, if it exists, would look very different from Earth. Plants might appear black or purple to absorb as much of the weak light as possible. The sky would not be blue, but a hazy salmon pink turning to dark purple at the edges of the eternal sunset. The search for life in this system is further complicated by the history of the stars themselves. Alpha Centauri A and B are slightly older than the Sun, roughly 5 to 6 billion years old. This means that any life on planets orbiting them would have had a head start on evolution. If stable planets exist around the primary pair, and the search continues, with tantalizing hints of a Neptune-sized planet in the habitable zone of Alpha Centauri A, they would have enjoyed a stable stellar environment for longer than Earth has existed. The metallicity of the stars, their richness in elements heavier than helium, is higher than that of the Sun. This suggests that the protoplanetary disk from which they formed was rich in the building blocks of rocky planets. The ingredients are there. The time is there. The stability, at least for the binary pair, is there. Yet, we must confront the Fermi paradox in the context of our nearest neighbors. If Alpha Centauri is older, and if it has planets, and if those planets are stable, why is the radio silence so deafening? We have pointed our radio telescopes at these stars for decades. We have listened for the leakage of radar, the pulse of communications, the deliberate signals of a civilization. We have heard nothing but the static of stellar processes. This silence forces us to consider the possibility that while planets are common, life is rare, or that technological civilizations are fleeting. It adds a layer of urgency to the mission. We are not just going there to see if we can, we are going there to calibrate our understanding of the probability of our own existence. If we find life next door, it means the universe is teeming. If we find a sterile system, it suggests we may be terrifyingly alone. The scale of Alpha Centauri also serves as a calibration for the scale of the galaxy. We speak of 4 light-years as a vast distance, yet it is merely the width of our front porch in galactic terms. The Milky Way is 100,000 light-years across. To reach Alpha Centauri is to take a single step out of our house. If we cannot master the physics and the economics to take this single step, we are imprisoned. The challenge of Alpha Centauri is the challenge of becoming an interstellar species. It is the great filter that stands between us and the rest of the universe. It demands that we master energy production on a planetary scale. It demands that we master materials that can withstand the fury of relativistic travel. It demands that we master the patience to plant trees under whose shade we will never sit. Let us consider the orbital mechanics of the B star again, for they present a unique opportunity for observation. Because the plane of the binary orbit is tilted relative to our line of sight, we do not see them eclipse each other. However, the gap between them on the sky is wide enough that we can resolve them as separate points of light, even with modest telescopes. This separation allows us to study the interactions of their stellar winds. When the stars approach their periastron, the point of closest approach, the collision of their stellar winds creates a shockwave of X-rays, a localized storm of high-energy particles that gives us a laboratory to study plasma physics on a stellar scale. This interaction also scrubs the inner regions of the system of dust, potentially making the view from any planets orbiting A or B clearer than the view from Earth, where we look through the zodiacal dust of our own system. The potential for moons around gas giants in the Alpha Centauri system offers another avenue for habitability. While a gas giant itself might be hostile, a large moon orbiting it could possess a thick atmosphere and be kept warm by tidal heating, similar to Europa or Enceladus in our own system, but magnified by the warmer environment of the temperate zone. Imagine a Pandora-like world, orbiting a Neptune-class giant around Alpha Centauri b. The sky would be dominated by the primary planet, a massive crescent hanging motionless in the sky, while the orange sun rises and sets, and the bright yellow companion star, Alpha Centauri A, acts as a distant lantern, casting double shadows and complicating the tides of the alien oceans. The complexity of the tides on such a moon would be immense, driven by the moon's orbit around the planet, the planet's orbit around the star, and the distant pull of the second star. These tides would churn the oceans and flex the crust, driving volcanism and recycling nutrients, potentially creating a cradle for life far more dynamic than the steady rhythm of Earth. The scientific yield from a mission to Alpha Centauri would extend far beyond planetary science. It would offer a baseline for stellar astrophysics that we cannot achieve from within the solar system. By measuring the precise parallax of distant objects from the vantage point of Alpha Centauri, we would extend the baseline of our triangulation of the universe. Currently, our baseline is the diameter of Earth's orbit, 2 astronomical units. By placing an observatory at Alpha Centauri, we would extend that baseline to nearly 300,000 astronomical units. This would allow us to measure the distance to stars across the galaxy and even to nearby galaxies with unprecedented precision, refining our understanding of the Hubble constant and the expansion rate of the universe. The system becomes a second eye for humanity, giving us true binocular vision of the cosmos for the first time. Navigating to this system requires a level of precision that borders on the impossible. At a distance of 4 light-years, a navigational error of a fraction of a degree results in missing the system by millions of kilometers. The guidance systems of the interstellar probes must be autonomous. The light speed lag means that Earth cannot steer the ship. If the probe detects an obstacle or needs to adjust its trajectory to intercept a planet, it must make that decision itself, using onboard AI that has been trained to recognize the gravitational signatures of the target system. This requires a shift in how we design space missions, moving from a command and control model to a fire and forget model where the spacecraft is an independent agent. The cultural impact of the arrival at Alpha Centauri will be as significant as the scientific one. For the first time, humanity will look at a picture of a sunrise from the surface of another world orbiting another star. That image, transmitted across the void, will rewrite our place in the narrative of creation. It will be the 21st century's Earthrise, a symbol of our reach and our fragility. It will prove that the distances, while vast, are not insurmountable. It will demonstrate that the laws of physics are not a cage, but a puzzle to be solved. The psychological barrier of the light year will be broken, and the galaxy will open up not as a backdrop, but as a territory. We must also consider the potential hazards of the destination itself. The stellar environment of Alpha Centauri is richer in heavy elements than our solar system. This implies a higher density of asteroids and comets. The cleanup of the system by the binary dynamics might not be as thorough as we hope. A probe traveling at 20% of the speed of light that encounters a dust cloud at the destination would be destroyed before it could transmit a single byte of data. The braking maneuver, if we ever choose to send a mission that stops, requires technologies we can scarcely imagine, perhaps using magnetic sails to drag against the interstellar medium or using the photons of the target stars themselves to decelerate. A manned mission, the ultimate dream of science fiction, remains centuries away, requiring generation ships or suspended animation technologies that are currently the realm of speculation. But the robotic precursors are within our grasp. The economic cost of such an endeavor is often cited as a barrier, but in the context of global economics, it is manageable. The cost of a Starshot-style infrastructure is estimated to be comparable to the budget of the Apollo program or the construction of the Large Hadron Collider. It is a question of allocation, not capability. It requires a species-wide decision to invest in a legacy that will not pay dividends for a generation. It is the construction of a cathedral, where the architects who lay the foundation will not live to see the spire. This long-term thinking is perhaps the most difficult challenge of the mission, harder than the lasers, harder than the sails, harder than the vacuum. It requires a shift in the human temporal horizon. Let us delve deeper into the specific atmospheric modeling of Proxima b, as this represents the most tangible target for our astrobiological aspirations. The interaction between a red dwarf's radiation and a planetary atmosphere creates exotic chemical pathways. The high ultraviolet flux can dissociate water molecules, leading to the escape of hydrogen and the buildup of oxygen. This could lead to a mirage Earth, a planet with a thick oxygen atmosphere that is nonetheless lifeless, the oxygen being a product of stellar destruction rather than biological creation. Distinguishing between a biotic oxygen signature and an abiotic one will require the detection of other biosignatures, such as methane or nitrous oxide, in specific ratios that chemical equilibrium cannot explain. The instruments on our flyby probes must be tuned to detect these subtle imbalances, sniffing the alien air at a velocity of 60,000 kilometers per second. The magnetic environment of the binary pair A and B also presents a fascinating puzzle. As the two stars orbit, their magnetospheres interact, potentially accelerating particles to energies that rival the most powerful accelerators on Earth. This could create a lethal radiation environment for any planets in the system, stripping away ozone layers and mutating surface life. However, a strong enough planetary magnetic field could create an auroral display that defies description, a sky constantly set ablaze with shimmering curtains of green and violet, driven by the winds of two suns. The aesthetic beauty of such a world would be matched only by its hostility. We must also look at the dust. The Alpha Centauri system appears to have a debris disk, a ring of dust and rock similar to our Kuiper belt. The presence of this dust is inferred from the infrared excess of the stars. This dust is the leftover material from planet formation, and its distribution can tell us where hidden planets might be lurking. A gap in the dust ring indicates a planet sweeping out its orbit. Mapping this dust structure is a primary goal of future space telescopes, like the Nancy Grace Roman Space Telescope, which will attempt to directly image the larger planets of the system by blocking the light of the stars with a chronograph. The narrative of Alpha Centauri is also a narrative of the history of science fiction becoming science fact. For a century, writers have populated these planets with civilizations, empires, and monsters. Now, as we approach the capability to actually visit, the reality is replacing the fiction. The planets we find may be dead, rock and ice, but they are real. They have topography, geology, weather. They are places, not plot points. The transition from imagination to cartography is a profound moment in the maturation of a civilization. We are mapping the coastline of the great ocean, preparing to push off from the shore. Every photon of light we collect from Alpha Centauri is 4 years old. We are looking at a ghost of the past. But when we send a probe, we are sending a piece of our present into the future. The probe becomes a time capsule, preserving the technology and the intentions of the launch generation for the arrival generation. It is a handshake across time. The signal that returns will be received by computers that have not yet been built, analyzed by scientists who have not yet been born. This temporal aspect of the mission binds the generations together in a common purpose, a thread of continuity that runs through the chaotic tapestry of human history. The sheer density of matter in the Alpha Centauri system, particularly in the core of the binary, suggests that if planets formed there, they might be super-Earths, rocky worlds with masses several times that of our own. The gravity on such a world would be crushing, perhaps 50% higher than on Earth. Mountains would be lower, slumped under the weight. The atmosphere would be compressed, denser at the surface. Life, if it evolved there, would be squat, robust, built to withstand the pull of the planet. The flora and fauna would be structurally different from anything on Earth, evolved to cope with high gravity and the specific spectrum of the star. As we refine our measurements, the wobble of Alpha Centauri b continues to tease us. The radial velocity method, which detects the slight back-and-forth motion of a star caused by the gravity of an orbiting planet, has pushed the limits of our technology. We are looking for a motion of mere centimeters per second, a slow walking pace, across 4 light-years. The noise in the data, caused by the bubbling surface of the star itself, mimics the signal of a planet. Disentangling the star's activity from the planet's pull is a statistical nightmare, requiring years of continuous observation. It is a search for a needle in a haystack, where the haystack is made of fire and is constantly shifting. The concept of panspermia also gains new relevance with Alpha Centauri. The exchange of material between our solar system and theirs is not impossible over billion-year timescales. Rocks blasted off Earth by asteroid impacts could theoretically drift across the void and seed the Alpha Centauri system, or vice versa. We could be looking for our cousins. Finding DNA-based life on Proxima b would be the ultimate twist, suggesting that life is not just universal, but that we are part of a specific galactic lineage, a diaspora of biology that spans the stars. Ultimately, the scale of Alpha Centauri is the scale of our ambition. It is the measuring stick against which we judge our maturity as a technological species. It stands there, bright and mocking in the southern sky, daring us to cross the abyss. It is the first rung on the ladder that leads out of the gravity well, out of the solar system, and into the infinite. To ignore it is to accept that we will die in the cradle. To reach for it is to declare that we intend to survive. The journey is long, the physics are unforgiving, and the cost is high. But the prize is nothing less than the galaxy itself. To understand the specific destination we aim for, we must look past the red dwarf Proxima and focus on the gravitational anchors of the system, Alpha Centauri A and Alpha Centauri B. While Proxima gets the headlines for its Earth-sized planet, the primary binary pair offers a more stable, albeit complex, environment that challenges our understanding of planetary formation. These two stars are locked in a gravitational embrace that defines the entire region, orbiting a common center of mass with a period of roughly 80 years. This is a human lifetime. If you were born on a planet orbiting Alpha Centauri A during its closest approach to B, you would be an old man by the time the two stars returned to that same configuration. The shape of this orbit is not a neat circle, but a highly eccentric ellipse, meaning the distance between the two suns varies drastically. At their closest, known as periastron, the two stars are separated by 11 astronomical units, roughly the distance between our Sun and Saturn. At their furthest, or apastron, they drift apart to 35 astronomical units, comparable to the distance to Pluto. This dynamic oscillation creates a gravitational environment of immense complexity. For a planet to survive here, it must thread a needle. If it orbits too far from its parent star, the gravity of the sibling star will destabilize it, flinging it out into the frozen dark of interstellar space or dragging it into a fiery collision. The stable zones are tight, hugging close to each star, forcing any potential worlds to huddle near the warmth for safety against the gravitational tides of the binary dance. The primary star, Alpha Centauri A, is a near-perfect twin of our own Sun. It is a G-type main sequence star, heavily enriched with metals, slightly more massive, and slightly more luminous than Sol. If you were to stand on the surface of a hypothetical world in its habitable zone, the light hitting your retina would feel hauntingly familiar. It would have the same white-yellow hue, the same intensity, and the same warmth that triggers the biological memories of 1 billion years of evolution on Earth. It is this similarity that makes Alpha Centauri A so seductive to astronomers and futurists alike. It represents a second chance, a mirror image of our home where the physics of the star itself does not present the violent, flaring volatility of a red dwarf. It is a calm, steady nuclear furnace that has been burning for perhaps even longer than our own Sun, offering a stable energy output that is the prerequisite for the slow, precarious rise of complex intelligence. Its partner, Alpha Centauri B, is a different beast entirely. It is a K-type main sequence star, smaller and cooler, burning with a distinctly orange light. It emits only half the luminosity of the Sun, meaning its habitable zone is much closer in. A planet orbiting B would experience a year lasting only days or weeks, whizzing around its star to maintain temperature. The light on such a world would be softer, shifting the color palette of the landscape. Photosynthetic life here, if it exists, might not be green. To absorb the peak energy of an orange star, foliage might evolve to be red, yellow, or even black, hungrily soaking up the dimmer photons. The sky would not be the piercing blue of Earth, but perhaps a darker, duskier shade, perpetually caught in the lighting of a late autumn afternoon. Imagine standing on a world orbiting Alpha Centauri B. The primary sun in your sky is the orange orb of B, hanging large and steady. But the sky contains a second sun. Alpha Centauri A would appear as a brilliant point of light, far brighter than the full moon on Earth, yet small enough to be resolved as a dazzling diamond rather than a disk. It would cast sharp shadows, creating a world of double shadows where night is rarely absolute. Depending on the alignment of the planets and the stars, you might experience periods where one sun sets just as the other rises, bathing the world in a perpetual twilight, a civilizational insomnia where the concept of day and night dissolves into a continuous shifting gradient of illumination. The constellations, however, would remain largely the same. The distance of 4 light-years is a mere step across the street in galactic terms, not enough to significantly shift the positions of the distant giants like Betelgeuse or Rigel. The Southern Cross would still point the way, and Orion would still hunt across the equator. But there would be one jarring addition, a new intruder in the ancient tapestries of the sky. In the constellation of Cassiopeia, near the heart of the Celestial Queen, a new star of first magnitude would blaze. It would be one of the brightest stars in the sky. A yellow-white beacon marking the location of a small, unremarkable G-type star. That star is the Sun. From the surface of Alpha Centauri, Earth is invisible, lost in the glare, but Sol is a prominent landmark. To look at it would be to look at history, to see the light that left humanity 4 years ago. It is a sobering thought that the entirety of human history, every war, every love affair, every monument, is contained within the gravitational well of that single bright dot in Cassiopeia. This perspective shift is the true value of the journey. It forces a Copernican revolution of the mind. Seeing the Sun as just another star in the sky, indistinguishable from thousands of others save for its brightness, strips away the last vestiges of geocentrism. It is visual proof of our mediocrity in the grand scheme, a realization that is both terrifying and liberating. We are not the center. We are merely neighbors in a crowded block of the Milky Way, looking across the fence at the lights next door. While our current obsession lies with propulsion, how to build the lasers, the sails, or the antimatter engines to bridge the gap, there is a darker, more difficult problem that receives far less attention: stopping. In the vacuum of space, Newton's first law is absolute. An object in motion stays in motion. If we accelerate a spacecraft to 20% of the speed of light to reach Alpha Centauri in a human lifetime, that spacecraft possesses an enormous amount of kinetic energy. Upon arrival, it does not simply glide into orbit. It screams through the system at 60,000 kilometers per second. At that speed, you would cross the distance from the Earth to the Moon in just over 6 seconds. If you do not shed that speed, you will traverse the entire Alpha Centauri system in a matter of hours, flying past the planets you traveled decades to see, unable to stop, unable to turn, destined to hurtle out into the deep void beyond, a ghost ship lost to the dark. Deceleration is the tyrant of interstellar mission planning. You cannot carry enough fuel to slow down with rockets. The rocket equation is unforgiving. To carry fuel to brake, you need fuel to accelerate that fuel, and fuel to accelerate the fuel that accelerates the fuel. The mass ratios become impossible. Therefore, we must use the environment itself to apply the brakes. One proposed solution is the magnetic sail, or magsail. This involves deploying a loop of superconducting wire hundreds of kilometers wide, generating a massive magnetic field. As the spacecraft plunges into the interstellar medium surrounding Alpha Centauri, this magnetic field interacts with the thin plasma of space, creating drag. It is an act of celestial aerodynamics, using the friction of the galaxy itself to claw back the velocity. As the ship gets closer, it can interact with the stellar wind of the stars themselves. Alpha Centauri A and B pump out streams of charged particles, a solar wind that blows outward into space. A spacecraft could ride this wind like a reverse kite, using the pressure of the star's own breath to push against its forward momentum. But the timing must be exquisite. The braking maneuver would need to begin years before arrival. A slow, agonizing deceleration that subjects the ship and its crew or instruments to variable forces. A miscalculation of the density of the interstellar medium or an unexpected lull in the stellar wind would result in a catastrophic overshoot. There is no air traffic control to correct the course. The onboard computers must be autonomous, sensing the invisible currents of space and adjusting the magnetic geometry in real time, executing a maneuver of unimaginable precision after 40 years of dormancy. The space between the Sun and Alpha Centauri is often depicted as empty, a perfect vacuum where nothing exists. This is a misconception. The void is not empty, it is merely thin. It is filled with the interstellar medium, a soup of hydrogen atoms, helium, dust grains, and high-energy cosmic rays. For a ship traveling at relativistic speeds, this medium transforms from a vacuum into a wall. At 20% of the speed of light, a single grain of dust, no larger than a speck of sand, hits with the force of a hand grenade. The erosion of the spacecraft's forward shield would be constant, a ceaseless sandblasting by the atoms of the universe. This creates a unique engineering challenge. The deflector. We are not just building a ship, we are building a plow. The forward section of any interstellar vehicle must be armored, layered with materials designed to ablate and absorb impacts. We might use blocks of ice, beryllium, or exotic aerogels to catch the dust and dissipate the heat. The friction of colliding with stray hydrogen atoms at relativistic speeds generates hard radiation, bathing the ship in a shower of gamma rays and X-rays. The crew, or the delicate electronic brains of the probe, must hide behind the bulk of the ship, sheltering in the shadow of the shield. This journey is not a silent glide. It is a violent, high-energy tunneling event through the fabric of the galaxy. Furthermore, the silence includes the electromagnetic spectrum. As the ship moves further away, the Sun becomes quieter. The chatter of Earth's radiosphere fades into the background noise. Communication becomes the ultimate bottleneck. To send a picture back from Alpha Centauri requires a transmitter of immense power or a receiver on Earth of immense size. We might need to build optical telescopes the size of cities, or use the Sun itself as a gravitational lens to focus the faint laser signals coming from the probe. The data rate would be trickles, bits per second, painful and slow. A high-resolution image of a Centaurian continent might take weeks to download packet by packet across the 4-light-year abyss. We will be waiting by the receiver like monks in a scriptorium, transcribing the holy text of a new world one letter at a time. If the mission is unmanned, these are problems of engineering. If the mission carries humans, they are problems of survival. The scale of Alpha Centauri forces us to confront the limitations of the human animal. We evolved in a 1G environment, protected by a thick atmosphere and a strong magnetic field, governed by a 24-hour circadian rhythm. Deep space offers none of this. To send humans to Alpha Centauri is to sever the biological tether that connects us to our evolutionary history. A generation ship, a vessel designed to house a community of humans for decades or centuries, is not just a vehicle. It is a closed ecological loop. Every breath of air must be recycled, every drop of water purified, every gram of waste reclaimed. The thermodynamics of such a closed system are precarious. Entropy is the enemy. A slow leak, a bacterial bloom in the algae tanks, a failure in the phosphorus cycle, any of these could spell a slow, suffocating death for the crew. We are talking about keeping a miniature biosphere alive in a tin can, surrounded by absolute zero for a duration longer than the existence of most nations on Earth. Then there is the psychological toll. The first generation of travelers, the ones who volunteer, will have the fire of mission and purpose. They are the explorers, but what of their children? The second generation born in the void, will have never seen a blue sky, never felt rain, never walked on a beach. They will be citizens of the corridor and the bulkhead. They will know Earth only as a myth, a bright star in the telescope, a story told by their parents. They will be trapped in a destiny they did not choose, hurtling toward a world they might not live to see. The sociology of the generation ship is the sociology of a prison, a monastery, and a lifeboat all at once. How does culture evolve in isolation? How does language drift? Does the mission itself become a religion, the original flight plan a sacred text that must be obeyed? The isolation creates a phenomenon known as the break-off. At a certain distance, Earth ceases to be a reality and becomes an abstraction. The delay in communication reinforces this. When you say hello and have to wait 8 years for a response, conversation is impossible. You are not talking to Earth. You are leaving messages on a grave. The crew of an Alpha Centauri mission will be the most solitary human beings to ever exist, completely divorced from the zeitgeist of the species. They will be a splinter civilization, drifting in the dark, evolving on their own trajectory. By the time they arrive, they may be as alien to us as the world they land on. Before we send ships, we send our eyes and ears. The scale of our interest in Alpha Centauri is matched by the intensity of our scrutiny. We are not just looking for microbes. We are looking for mirrors. In the search for extraterrestrial intelligence, or SETI, Alpha Centauri is the primary target for the detection of technosignatures, evidence of advanced technology. If a civilization exists there, or ever existed there, it might have left a mark visible across the light years. We scan the radio spectrum for leakage. Just as Earth leaks radar, television, and radio waves into space, a technological society on a planet around Alpha Centauri b might do the same. We listen for the structured hum of carrier waves, the mathematical pulsing of navigation beacons, or the collimated burst of laser communications. But we also look for more subtle signs. We look for the spectral fingerprint of industrial pollution in the atmosphere, chlorofluorocarbons, artificial compounds that do not occur in nature, would be a smoking gun. If we detect the spectral absorption lines of complex industrial chemicals in the atmosphere of a Centaurian planet, we will know that someone is there, breathing the smog of their own progress. We also look for the infrared excess that signals megastructures. If a civilization has expanded into space, they might be harvesting the energy of their star with vast solar arrays, swarms of satellites that block and re-radiate the starlight as heat. This concept, a variation of the Dyson sphere, would alter the light curve of the star. We watch Alpha Centauri A and B with unblinking vigilance, looking for the telltale dip in brightness that cannot be explained by a planet, a dip that suggests something artificial, geometric, and massive is passing in front of the star. Even the absence of a signal is data. The great silence from our nearest neighbor is a profound observation. If Alpha Centauri, a system older than ours, is empty of high-technology civilizations, it tells us something about the rarity of intelligence or the longevity of technical societies. It suggests that the hurdle to becoming a spacefaring species is incredibly high, or that civilizations tend to destroy themselves before they can colonize even their nearest stellar neighbor. The silence of Alpha Centauri acts as a mirror, forcing us to question our own longevity. If they are not there, why are we? And how long will we last? The path to Alpha Centauri is paved with precursor missions. We will not jump from low Earth orbit to a starship in one bound. The scale of the challenge demands a ladder of increasing ambition. We are already seeing the first rungs being built. The Voyager probes, though not aimed at Centauri, taught us about the heliopause, the boundary where the sun's influence gives way to the interstellar medium. New mission concepts, like the interstellar probe proposed by Applied Physics Labs, aim to go 10 times further than Voyager, reaching out to 1,000 astronomical units to taste the pristine interstellar cloud. These precursors are essential for mapping the terrain. We need to know the density of the dust, the strength of the magnetic fields, and the intensity of the cosmic rays before we can design the shields for a relativistic starship. We need to understand the Oort cloud, the vast shell of comets that surrounds our solar system and presumably surrounds Alpha Centauri as well. Traversing this cloud is like navigating a minefield. We need to know the distribution of the debris. Every telescope we build is a virtual ship. The extremely large telescope currently under construction in the deserts of Chile will have the resolution to directly image planets in the habitable zones of the Alpha Centauri stars. For the first time, we will not just infer their existence from wobbles in the data, we will see them as photons, distinct points of light separate from their stars. We will analyze their light for oxygen, methane, and water vapor. We will make the journey with optics before we make it with engines. This remote reconnaissance is the first phase of the invasion, the gathering of intelligence that will determine where we land and what we prepare for. The scale of Alpha Centauri is ultimately a test of our patience. It is a project that spans generations. The scientists who design the mission will not be the ones to launch it. The ones who launch it will not be the ones to receive the signal of arrival. It requires a continuity of purpose that is rare in human history, akin to the construction of the great cathedrals of Europe, where the masons laying the foundation knew they would never see the spire. We are laying the foundation now. The physics are worked out, the engineering is conceptualized, and the targets are identified. The only variable remaining is the will to commit resources to a payoff that lies centuries in the future. Reaching Alpha Centauri may require us to break physics as we know it, or at least push it to its absolute breaking point. The conventional methods, chemical rockets, ion drives, even nuclear thermal propulsion, are simply too slow. To cross the void in a human lifetime requires energy densities that border on the fantastical. We are forced to look at the edges of theoretical physics for answers. Antimatter is the most potent fuel in the universe. When matter meets antimatter, the conversion to energy is 100% efficient, according to Einstein's E = mc². A few kilograms of antimatter could power a starship to Alpha Centauri, but the cost of producing it is currently astronomical, and the danger of storing it is existential. A containment failure would result in a detonation equivalent to a strategic nuclear arsenal. Yet, it remains one of the few physics-compliant ways to achieve the necessary thrust. Then there is the fusion ramjet, the busted ramjet, a theoretical engine that scoops up the interstellar hydrogen as it flies, compressing it and fusing it to generate thrust. It is the dream of the infinite engine, a ship that requires no fuel tanks, because the galaxy itself provides the fuel. While the drag effects of the scoop currently make the math difficult, it represents the kind of radical thinking required to conquer the scale of the distance. We even flirt with the ideas of warp drives and Alcubierre metrics, manipulating the geometry of spacetime itself to bypass the light speed limit. While these remain firmly in the realm of theory, the very existence of Alpha Centauri drives the research. The target creates the necessity for the invention. Without a destination, there is no need for the engine. The star pulls the technology out of us, demanding that we solve the riddle of energy and mass to bridge the gap. In the end, Alpha Centauri is more than a star system. It is a destiny. It is the inevitable next step for a species that has filled every corner of its home planet. We have climbed the mountains, crossed the oceans, and mapped the continents. We have visited the moon and sent robots to the planets. The solar system is becoming a known quantity. The stars are the only remaining unknown, the only frontier left that offers the promise of the infinite. The scale of the distance is a barrier. Yes, but it is also a filter. It ensures that we cannot go until we are ready. We cannot reach Alpha Centauri as a warring, fractured species. The energy requirements, the global cooperation, and the long-term planning required for such a mission necessitate a level of planetary unity we have not yet achieved. The star stands as a graduation test. If we can organize ourselves to bridge that 4-light-year gap, we will have proven that we have matured past our adolescence. We will have proven that we can prioritize the survival of the species over the squabbles of the moment. To look at Alpha Centauri is to look at the future. It is there, waiting in the southern sky, a binary beacon calling out across the silence. It promises new worlds, new physics, and a new chapter in the story of life. The scale is vast, the journey is hard, and the outcome is uncertain. But the alternative is to stay here, trapped in the amber of our own history, until the sun eventually swells and swallows us whole. The choice is between the difficult impossible and the comfortable inevitable. Alpha Centauri is the difficult impossible, and that is why we must go.